Welcome to The Explainer. Today we're going to tackle a physics concept that trips up so many people, the difference between an electric field and electric flux. On the surface, it sounds pretty straightforward, but getting that real gut-level feel for it can be surprisingly tough.
And this comment from Reddit it hits the nail on the head, right? You can plug the numbers into the formula, but what are we really talking about? So you asked for an explain like I'm 5 version, and that is exactly what we're going to do. Let's start with a really simple analogy to build that intuition from the ground up.
All right, to really get a feel for this, we're going to borrow a fantastic analogy from another Reddit user. So for a minute, I want you to completely forget about physics, charges, and fields. Instead, let's just think about something way simpler: marbles and pipes.
Just picture this pipe. It's on a slope. Now the pipe itself isn't the action, is it? It's the potential for action. It just sits there. But because it's sloped, it creates this invisible influence that's going to force anything you put inside it to move in a very specific direction, downhill.
Okay, so here is how this whole thing breaks down. That sloped pipe, that's our electric field. It's that invisible area of influence. The marbles we drop in, those are our charged particles, the little things that are being pushed around by the field. And the flow, counting how many marbles pass a certain point every second, that is the electric flux. See the difference? It's a measure of how much stuff is actually moving through, not just the potential for it to move.
All right, so we've got our analogy down. Now, let's connect this idea of a pipe to the real-deal physics definition of an electric field.
And here's the absolute key. The electric field is the condition itself. It's just a property of the space around a charge, and we draw these imaginary lines to help us see it. Just like our sloped pipe, the field is just there. It exists all around the charge, whether or not another particle is actually there to feel its push or pull.
So if the field is the pipe, the potential for something to happen, then what in the world is flux in physics terms? How do we actually measure the flow of this invisible field?
Flux, when you boil it all down, is about counting. That's it. Imagine you're standing outside holding up a hula hoop while it's raining. The rain is falling everywhere. That's kind of like the field. But the flux, that's just the total amount of rain that actually passes through your hoop. It's not about the whole rainstorm. It's about what goes through one specific defined area.
And this gets to a really important distinction. The electric field is a vector. It has a strength and a direction at any single point in space. But flux is a scalar. It's just a number, a total count for a whole surface. One is about the condition at a point. The other is a measurement over an area.
So what changes that count? Well, it's basically 3 things. First, a stronger field. If it starts raining harder, more rain goes through your hoop, right? More flux. Second, a bigger surface area. If you use a giant hoop instead of a tiny one, you'll catch more rain. Again, more flux. But the angle is absolutely crucial. If you hold the hoop flat, perpendicular to the rain, you catch the most. But what if you turn it sideways, parallel to the raindrops? Nothing goes through it. Your flux is 0.
Okay, I know what you might be thinking. This is all a little abstract, right? Why do we even need this whole separate idea of flux? Well, this is where it gets really cool, because flux gives us a kind of superpower. Let's check it out with a fun little thought experiment.
This is a classic problem. Imagine you have a box. It is completely sealed. You can't open it, you can't peek inside, but you absolutely have to know if there's an electric charge hiding in there. How in the world do you do it? Well, this is where flux becomes our secret weapon.
Think of a positive charge as being like a tiny light bulb. If you put that light bulb inside a frosted glass box, you can't see the bulb itself, can you? But you can definitely see the light shining out from all sides. It's the exact same idea here. A positive charge inside our box creates a net outward flow or flux of electric field lines through the box's surface.
Now, a negative charge is the complete opposite. It acts like a sink or maybe a tiny vacuum cleaner, sucking those field lines inward. So if we measure the surface of our box and see that the net flow of field lines is into the box, we know for sure there's got to be a negative charge hiding inside.
So what happens if you have both, a positive charge and an equal negative charge right next to each other inside? Well, the field lines come out of the positive and go straight into the negative. For the box as a whole, any field line that comes in one side goes right back out the other. The flow in perfectly cancels the flow out. The net result? 0. Zip. Nada.
And that right there, that is the superpower. We never had to open the box. Just by measuring the net flow of the electric field through its outer surface, we can figure out the exact net charge that's sealed away on the inside. This incredibly powerful idea is the heart of something called Gauss's law.
Okay, let's bring this all together. We started with a simple idea about marbles in a pipe, and we ended up with a physical law that lets us basically see inside a sealed container. I mean, that's a pretty big leap when you think about it.
Honestly, this table is the ultimate cheat sheet for this whole topic. It connects every single part of our simple pipe and marbles analogy directly to the formal physics. The sloped pipe is the field, the marbles are the charges, the rate of flow is the flux, and, most importantly, knowing the total flow out of the pipe tells you something about the source of marbles up top, and that's Gauss's law in a nutshell.
And this all leads to a final, much bigger thought. This whole idea of flux, of measuring the flow of an invisible field through a surface, it's not just for electricity. It's a fundamental tool that's used to understand gravity, magnetism, how fluids flow, and so much more. So it kind of makes you wonder, right? If this one simple method lets us measure an invisible charge inside a box, what other hidden properties of our universe can we uncover just by observing their influence on the world all around us?